If something in the universe is so big that our entire solar system could fit inside it, should we even be able to see it? Because the moment you understand what this thing really is, the universe stops feeling safe in the way you thought it was. What I'm about to walk you through isn't a rumor, and it isn't science fiction. It's a real object astronomers have measured, cross-checked, and argued over for decades. And the numbers are so extreme that even the scientists who found it thought they had made a mistake. By the end of this story, you'll understand why this single object changed how we think black holes grow, how galaxies form, and how violent the early universe really was. Out there, more than 10 billion light-years from Earth, there's a source of light so powerful it outshines entire galaxies. That light left its home when our planet didn't exist yet, when the sun had not been born, when the Milky Way was still young and rough around the edges. That light crossed expanding space, drifting for most of the age of the universe, just to reach our telescopes. And when astronomers finally traced it back to where it came from, they realized they weren't looking at a star or even a galaxy. They were looking at a monster. To understand how big this thing really is, let's start at home. Look up at the night sky and find that pale white band stretching across the darkness. That's the Milky Way, our galaxy, with hundreds of billions of stars packed into a spinning disk. Near its center sits a black hole called Sagittarius A. Astronomers at the Harvard-Smithsonian Center for Astrophysics and NASA Jet Propulsion Laboratory have spent decades tracking the stars whipping around this invisible object. From those star orbits, they measured its mass, about 4 million times the mass of our Sunday. That sounds huge, and it is. Sagittarius A times holds our galaxy together like a pin through the center of a record. But now comes the part that messes with your sense of scale. Ton 618 is not 4 million suns. It's about 66 billion suns. That means the black hole at the heart of TON 618 is more than 16,000 times heavier than the one anchoring our entire galaxy. If you took Sagittarius A times and tried to build up to Ton 618 by stacking black holes on top of each other, you'd need thousands of Milky Way-sized centers to match it. Now let's talk size, not mass. A black hole's event horizon is the point where not even light can escape. For Ton 618, that boundary would stretch far beyond the orbit of Pluto if you placed it where our Sun sits. Not just past Earth, not just past Jupiter, not just past Neptune, way beyond the edge of our solar system. Every planet, every asteroid, every comet you've ever heard of would be inside the shadow of this one object. And yet, from Earth, Ton 618 looks like a tiny dot of light. When astronomers first spotted it in the 1950s, using surveys at the Keck Observatory in Mexico, they didn't know what it was. It looked like a strange blue star. Later, when researchers compared its spectrum using techniques refined with data from Hubble spectrograph records and radio surveys connected to Arecibo legacy data, they realized the light was wildly redshifted. The object was not nearby. It was unimaginably far away, so far that its brightness could only mean one thing. Something small was producing more energy than entire galaxies. That discovery shook astronomy in the 1960s. Objects like Ton 618 were given a name: quasars. And quasars became one of the biggest puzzles in space science. How could so much energy come from such a tiny region? The answer that slowly formed through work at places like the European Southern Observatory and Keck Observatory in Hawaii was brutal and elegant at the same time. A black hole feeding. TON 618 is what happens when a supermassive black hole goes into overdrive. Gas, dust, and entire stars fall toward it, forming a glowing disk that spins faster and faster as it spirals inward. Friction, magnetic fields, and gravity heat that material to insane temperatures. Before the matter disappears forever, it screams in light. X-rays, ultraviolet, visible light, infrared, radio waves. The James Webb Space Telescope has helped map how these distant quasars shine across time, while ground-based observatories measure how fast the material is moving. Here's the part most people miss. A black hole itself is dark. What blinds you is the meal. The disk of doomed matter around TON 618 shines with the power of about 140 trillion suns, not because the black hole glows, but because the space around it is being torn apart. If TON 618 were placed where our sun is, the light alone would boil Earth's oceans in minutes. Life wouldn't fade, it would be erased. And that leads to the question scientists still argue about today. How did something this big form so early in the universe? When TON 618's light started its journey toward us, the universe was young. Galaxies were still growing. Stars were still being born in chaotic bursts. According to many models built from Vera Rubin Observatory simulations and early galaxy surveys, black holes were supposed to grow slowly, star by star, gas cloud by gas cloud. But TON 618 is already enormous, when the universe is barely a fraction of its current age. That's a problem. It means either black holes can grow much faster than we thought, or something in the early universe helped them bulk up in ways we don't yet understand. Some astronomers suggest early black holes formed directly from collapsing gas clouds, skipping the small stages. Others think massive mergers happened again and again in crowded young galaxies. Teams using James Webb Space Telescope data are hunting for more giant quasars, like TON 618, to see if it's rare or just the first of many we're finally able to spot. Because if TON 618 isn't unique, then the early universe wasn't just chaotic. It was violent on a scale that rewrites how we picture cosmic history. And we're not done with the scary part yet. As we move closer to TON 618 inches this mental journey, the light grows brighter. The disk thickens into a storm of glowing plasma. Jets of energy shoot from the poles at near light speed, carving paths through surrounding space. These jets can stretch for hundreds of thousands of light years, punching through their host galaxies, shaping how stars form, heating gas, even starving regions of space of the material needed to make new suns. This one object doesn't just sit there. It controls its entire neighborhood. Entire galaxies live and die by how monsters like TON 618 behave. As we move closer in our imagination, the space around TON 618 stops behaving the way your brain expects it to. Distances stretch, time slows, light bends. This isn't poetry, this is physics. Einstein predicted it, and observatories like the Keck Observatory in Hawaii and teams working with data from the Hubble spectrograph records have confirmed these effects around black holes across the universe. TON 618 is just the extreme version of that reality. The disk of matter around TON 618 isn't a neat ring, it's a violent storm. Gas clouds slam into each other at thousands of kilometers per second. Magnetic fields twist and snap like overstretched wires. When those fields break and reconnect, they release sudden bursts of energy that light up the quasar in unpredictable flares. Astronomers at NASA Jet Propulsion Laboratory compare these events to solar flares, but on a scale so large, it makes our sun's worst storms look like sparks from a lighter. Now imagine what happens to a star that wanders too close. A normal star, like our sun, approaching TON 618 wouldn't fall in gently. Long before it reached the black hole itself, the difference in gravity between the near side of the star and the far side would tear it apart. This process is called spaghettification. The star would stretch into a long, glowing ribbon of gas. That gas would wrap around the black hole, crash into the disk, heat up, and then vanish past the point of no return. Telescopes guided by teams from the European Southern Observatory have caught glimpses of similar events in smaller black holes. Around TON 618, those same events would be brighter, faster, and far more violent. Here's the part that feels wrong when you first hear it. Black holes don't suck things in like cosmic vacuum cleaners. Space near them is not a whirlpool pulling everything nearby to its doom. If you kept a safe distance, you could orbit a black hole just like you orbit a star. The danger comes when you cross invisible boundaries. For TON 618, that boundary is massive. You could orbit peacefully far outside where Pluto would be, and everything would seem calm. But drift too close, and gravity takes over in a way nothing can fight. This is where time starts to play tricks. From far away, if you watch something fall toward TON 618, you would never see it cross the event horizon. The light from that object would stretch and fade, slowing down until it looked frozen at the edge. This effect has been measured indirectly around smaller black holes using X-ray timing data and spectral shifts, work supported by collaborations linked to NASA centers and university teams at places like Stanford. But for the falling object itself, time would feel normal. It would cross the boundary in moments and never know it happened. Two realities, both true, both impossible to fully picture. And then there's the size problem again. The event horizon of TON 618 is so huge that, in theory, you could cross it without being torn apart right away. The extreme tidal forces that rip you into a strand near smaller black holes are spread out near ultramassive ones. You wouldn't feel the stretching at first. You'd fall, quietly, silently, with no way back. Only later, deeper inside, would gravity become lethal. This is one of the creepiest facts about black holes of this scale. They are gentle at the door and deadly inside. So how do we even know TON 618 is this massive if we can't see the black hole itself? Astronomers use several clues. They measure how fast gas clouds orbit the center. They analyze how wide certain spectral lines are, which tells them how violently matter is moving. They estimate how bright the quasar is and work backward to figure out how much mass must be feeding the engine to produce that much energy. These methods were refined through decades of quasar studies, with data pipelines shared between observatories and research centers like the Harvard-Smithsonian Center for Astrophysics. Different teams using different methods all land on the same terrifying conclusion. TON 618 is one of the largest black holes we have ever found. And here's the part that should make you uneasy. We didn't go looking for the biggest black hole in the universe. We stumbled across it because it happened to be feeding loudly. That means there could be others just as big, or bigger, sitting quietly in the dark. No glowing disk, no bright jets. Just massive shadows drifting through space, invisible to our telescopes unless something lights them up. The universe doesn't advertise its biggest dangers. It hides them until they move or feed. As more sky surveys come online, like the Vera Rubin Observatory's wide-field scans, astronomers expect to find more extreme objects. Not because they're new, but because we are finally building eyes wide enough to notice them. TON 618 might be rare, or it might be the first giant we've learned how to recognize. And that leads to a deeper question scientists are still wrestling with. If objects like TON 618 existed so early, what did they do to the young universe? Did they help shape galaxies, or destroy them before they could grow? We're only beginning to understand how monsters like this sculpted the cosmic landscape we live in today. Now, zoom out for a second and look at the bigger picture. TON 618 isn't just a freak object sitting alone in space. It lives inside a young galaxy that existed when the universe was still in its chaotic teenage years. Back then, galaxies were crashing into each other all the time. Gas was everywhere. Stars were being born fast and dying young. It was messy, loud, and violent. Perfect conditions for building monsters. When galaxies collide, their gas clouds slam together. That gas loses energy, falls toward the center, and feeds whatever black hole is waiting there. This is how small black holes grow into supermassive ones. But TON 618 didn't just grow big, it grew fast. So fast that it's making scientists at places like the Harvard-Smithsonian Center for Astrophysics and teams working with data from the James Webb Space Telescope ask hard questions about our models of the early universe. Here's the problem. According to standard models, black holes grow at a limited rate. There's a natural speed limit set by physics. If a black hole eats too fast, the radiation it produces pushes new material away. It's like trying to drink from a fire hose that's blasting back in your face. This limit is called the Eddington limit. For most black holes, it caps how quickly they can gain mass. But TON 618 seems to have ignored that rule. To reach 66 billion times the mass of the Sun in such a young universe, it either started life already huge, or it found a way to feed far beyond what our models say should be possible. Some researchers think early black holes may have formed directly from the collapse of giant gas clouds, skipping the slow star-to-black hole phase. This idea has been explored in theoretical work supported by data from the European Southern Observatory and modeling groups linked to NASA Jet Propulsion Laboratory. If that's true, then the early universe may have been filled with black hole seeds already millions of times the mass of our Sunday. Another idea is that black holes like TON 618 grew through non-stop mergers. Smaller black holes fell together again and again as galaxies smashed into each other. Each merger added mass. Each collision fed the center more gas. Over hundreds of millions of years, this could build something truly extreme. The problem is timing. Even with constant feeding and merging, TON 618 still looks too big, too early. So scientists are stuck with an uncomfortable truth. Either our growth models are incomplete, or the early universe was wilder than we thought. Now let's talk about what TON 618 is doing to its own galaxy. A quasar this powerful doesn't just sit quietly. It blasts energy into its surroundings. Jets of particles shoot out near light speed. Radiation floods the galaxy. This can actually shut down star formation. Gas that would have become new stars gets heated and blown away. In some galaxies, this feedback seems to regulate growth. The black hole grows, then it starves its own galaxy by pushing fuel away. Astronomers have seen this balance in closer systems using instruments tied to the Keck Observatory and space-based X-ray telescopes. TON 618, though, is on another level. Its energy output is so massive that it could strip gas from huge regions of its host galaxy. In simple terms, it may have grown so powerful that it began to kill its own food supply. This is one reason quasars don't stay bright forever. They burn hot, then fade as they run out of fuel. Somewhere out there, TON 618 may already be quieter than it was when the light we see today left it. And remember that part. The light reaching us now started its journey about 10 billion years ago. What we're seeing is not TON 618 today. We're seeing it as it was when the universe was young. Right now, in real time, that system could look totally different. The quasar might be dim, the black hole might be starving, or the galaxy might be torn apart by forces we can't yet imagine. Every image we take of deep space is a fossil record. We are cosmic archaeologists, piecing together a story from light that left before Earth even existed. This brings us to something quietly unsettling. We live in a universe where monsters like TON 618 formed naturally. No design, no intention, just gravity, time, and chaos. The same laws that made our sun also made something that could swallow our entire solar system and not even notice. The universe doesn't care about scale. It doesn't care about comfort. It just follows its rules, even when those rules build things that feel like nightmares to the human mind. And here's the kicker. TON 618 is not the end of the story. It's just the biggest one we've measured so far. There's a quiet question hiding behind all of this. If TON 618 can exist, how many others like it are out there that we haven't seen yet? Our telescopes only catch the brightest quasars. We spot the ones screaming across the universe, blasting energy in every direction. But for every blazing monster we see, there could be dozens or hundreds that are quieter, hidden by dust, angled away from us, or simply too far and faint to detect. Teams using deep sky surveys connected to projects like the Vera Rubin Observatory are preparing to map huge parts of the sky again and again, looking for tiny changes in light that reveal distant quasars and active black holes. What we know right now is almost certainly just the tip of the iceberg. This matters because black holes shape the universe more than most people realize. They control how galaxies grow. They shape where stars can form. They influence how matter moves on the largest scales. At the centers of most big galaxies, including our own Milky Way, sits a supermassive black hole. Ours is called Sagittarius A, and it's been studied in detail by teams using data from the Event Horizon Telescope and observatories tied to ESO. It weighs about 4 million suns. That sounds insane until you compare it to TON 618. Then Sagittarius A time starts to look small. But even small supermassive black holes quietly guide how galaxies evolve over billions of years. Now picture the early universe again. Young galaxies forming, gas flowing everywhere, dark matter shaping invisible scaffolding across space, as mapped by large surveys and simulations run by university groups and space agencies. In the centers of many of these newborn galaxies, black holes are switching on like cosmic engines. Some stay modest, some become monsters. The biggest ones, like TON 618, light up the universe so brightly that they become landmarks across cosmic time. This is one reason quasars were so important to early astronomy. Before we had powerful telescopes, quasars were among the few things bright enough to be seen from the edge of the visible universe. Data from early radio surveys, including legacy Arecibo observations, helped scientists realize these were not stars at all, but distant galaxies with insane energy sources at their cores. That realization changed cosmology forever. It told us the universe was bigger, older, and more violent than we imagined. But here's where the story gets personal. TON 618 forces us to face how small our sense of big really is. We think in planets. We stretch to stars. We struggle with galaxies. But black holes like this blow past all of that. If TON 618 replaced our Sun, its event horizon would swallow Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto, and still keep going far beyond. The orbit of Pluto would be deep inside the darkness. Light itself would have no chance to escape once it crossed that boundary. There would be no dramatic pull from far away. The planets wouldn't suddenly get ripped apart from across the solar system. Gravity at a distance depends on mass, and a black hole of the same mass as the Sun would pull the same way. But TON 618 is not the same mass. It's tens of billions of times heavier. The solar system as we know it would not exist in any stable way around such an object. And yet, TON 618 is just doing what gravity does. No anger, no intent, no hunger in the human sense. Just matter following curved space and time, exactly as Einstein described. Teams at places like Stanford and researchers building models of black hole physics keep pushing these equations to their limits, trying to see how far general relativity can be trusted under such extreme conditions. So far, it keeps working. That alone is wild. A theory written over a century ago still describes objects that outshine entire galaxies. Now, there's another strange detail. TON 618 is so bright that it becomes a backlight for the universe. The light passing through space gets absorbed by gas clouds between us and the quasar. By studying these absorption lines with tools like Hubble's spectrograph and ground-based telescopes, scientists can map what the universe was made of billions of years ago. We learn where hydrogen was thick, where metals were forming, where early galaxies were enriching space with heavy elements. TON 618 is not just a monster, it's a flashlight shining through cosmic fog, which means every terrifying object also becomes a tool. The same thing that could erase entire star systems if you got too close is helping us understand how the universe grew up. That's the strange balance of space science. The scariest objects often teach us the most. And we're not done yet. Let's go one layer deeper into how something like TON 618 even gets the chance to exist, because this part still bothers scientists. To build a black hole that massive, you need two things: a huge starting seed and a steady supply of food for a very long time. The problem is, the early universe didn't seem to give enough time for normal black holes to grow this big using the slow, steady process we understand. Even if a black hole eats as fast as physics allows, there's a limit called the Eddington limit. Push past it, and the radiation blowing outward should choke off the flow of matter falling in. It's like trying to drink from a fire hose that pushes back. And yet, TON 618 and other ultra-massive black holes were already huge when the universe was still young. So how did they cheat the system? Researchers at places like the Harvard-Smithsonian Center for Astrophysics and teams working with data from the James Webb Space Telescope have been exploring a few serious ideas. None of them are sci-fi. All of them stretch what we thought was normal. One idea is direct collapse. Instead of starting with a normal star that dies and leaves behind a small black hole, maybe some black holes formed when massive clouds of gas collapsed directly into black holes without ever becoming stars. No supernova. No slow buildup, just gravity winning all at once. This could create seed black holes thousands or even millions of times the mass of the Sun right from the start. If Ton 618 began life that way, it already had a massive head start. Another idea is superfeeding. In the early universe, galaxies were messy. Gas was everywhere. Collisions were common. Streams of matter flowed into galactic centers like rivers during flood season. Some black holes may have been fed almost non-stop for millions of years. The usual limits might be bent in these chaotic environments. Simulations run by astrophysics groups using supercomputers suggest that in certain extreme cases, black holes can grow faster than the clean, simple models predict. There's also the merger path. Black holes merge when galaxies collide. Small ones combine into bigger ones. Bigger ones combine into monsters. Over time, this stacking effect can build insane masses. We've already seen black hole mergers through gravitational waves detected by LIGO and Virgo. Those are small compared to Ton 618, but they show the process is real. Scale that up over billions of years, and you start to see how cosmic giants could form. But here's the part that keeps people up at night. Even with all of these ideas, Ton 618 still feels extreme. It sits right at the edge of what our models comfortably allow. It's not breaking physics, but it's pressing hard on the walls. And that's usually where new understanding begins. When something sits right on the edge of what should exist, it's often pointing at missing pieces in our picture of the universe. Now zoom out for a second. Think about what it means that this object exists at all. TON 618 is not rare in a human sense. It's rare in a cosmic sense. But the universe is so large that even rare things can exist many times over. The observable universe holds hundreds of billions of galaxies. If only 1 in a million galaxies hosts a black hole like Ton 618, that's still hundreds of thousands of cosmic monsters out there. And most of them are so far away that their light will never reach us. That's a hard thought to sit with. We live in a small pocket of a much larger story. Our Milky Way is one tiny swirl of stars in a cosmic web that stretches beyond anything the human brain evolved to picture. Ton 618 is a reminder that the universe doesn't scale to our comfort. It scales to its own rules. And yet, somehow, we get to see it. Now, let's talk about what it would actually be like if something this big were anywhere near us. Not just as a science idea, but as a real, physical neighbor. Ton 618 is so far away that it poses zero danger to us. It's about 10 billion light-years out. That distance isn't just far. It's so far that the light reaching us today left when Earth didn't even exist yet. So this isn't about fear. It's about perspective. But imagine for a moment a black hole, even a tiny fraction of this size, sitting in our own galaxy. The black hole at the center of the Milky Way, Sagittarius A, is already huge, about 4 million times the mass of the Sunday. Astronomers at the Max Planck Institute for Extraterrestrial Physics, working with the Event Horizon Telescope collaboration, have imaged its shadow. Even that small supermassive black hole controls the motion of stars tens of thousands of light-years away. Now compare that to TON 618. Ton 618 is more than 10,000 times more massive than Sagittarius A. If something like that replaced the black hole at the center of our galaxy, the structure of the Milky Way would look different. Stars would orbit faster near the center. Gas would heat more violently. The galaxy might shine brighter as the black hole fed. But here's the surprising part. Our solar system, way out in the suburbs of the galaxy, would still be fine. Gravity weakens with distance. The danger isn't size alone. The danger is closeness. Black holes don't go around hunting planets. They don't suck things in like vacuum cleaners. They only affect what gets very close. If our sun were magically replaced by a black hole of the same mass, Earth would keep orbiting almost exactly the same way. The disaster would come from losing sunlight, not from gravity. So the fear people often feel when they hear giant black hole is more emotional than physical. The real threat is not that black holes are evil cosmic monsters. The real threat is how extreme environments behave near them. Near TON 618, space itself is violent. Radiation levels are so high that atoms can't hold together. Magnetic fields twist like torn metal. Shock waves ripple through plasma hotter than any star core. Jets blast out along the poles, carrying energy across distances larger than galaxies. Observatories like the European Southern Observatory and radio arrays that build on Arecibo's legacy data have seen similar jets in other quasars. They can stretch hundreds of thousands of light years, carving paths through intergalactic gas. If a planet somehow existed near TON 618, it wouldn't just be burned, it would be ripped apart at the atomic level. Molecules would break, atoms would ionize. The very concept of surface would stop making sense. And yet, those same brutal forces shape galaxies. Quasars don't just destroy, they regulate. When a black hole feeds, it also blasts energy back into its galaxy. This can heat gas so much that new stars stop forming. In other cases, shock waves can compress gas and trigger bursts of starbirth. Black holes, in a strange way, act like cosmic thermostats. They help decide when galaxies grow and when they quiet down. This connection between black holes and galaxy growth is one of the big reasons teams at NASA JPL, the European Southern Observatory, and the Harvard Smithsonian Center for Astrophysics study objects like TON 618 so closely. It's not just about one extreme object, it's about how galaxies across the universe evolved. Because here's the deeper question hiding under all this. If black holes like TON 618 exist so early in cosmic history, then galaxies may have grown around black holes, not the other way around. That flips the story we used to tell. We used to think galaxies formed first, and black holes slowly grew inside them. Now, the data from Hubble spectrograph records and James Webb observations hint that giant black holes may have been there first, shaping galaxies from the inside out. It's like discovering the foundation was poured before the house was even designed. And that brings us to an uncomfortable idea. The universe may be far better at building extremes than we ever expected. That idea should make you pause for a second. Because if the universe can build monsters like TON 618 so early, so fast, then our models of how things grow are missing something big. Astronomers using the James Webb Space Telescope and the Keck Observatory in Hawaii are now finding massive black holes in galaxies that formed when the universe was still young. These objects appear far too large for the amount of time they've had to grow if they started from small stellar black holes. The math doesn't add up cleanly. Even if you feed a black hole at the maximum rate allowed by physics, called the Eddington limit, it shouldn't reach tens of billions of solar masses that quickly. So how did TON 618 get so huge? There are a few serious ideas on the table. One is that the first black holes didn't start small. Some researchers think giant clouds of gas in the early universe may have collapsed directly into massive black holes, skipping the normal star phase. This direct collapse idea is being studied by teams at the Harvard Smithsonian Center for Astrophysics and modeled with supercomputers that solve full general relativity equations. If true, TON 618 could be the grown-up version of one of those early giants. Another idea is that early black holes merged rapidly. In the young universe, galaxies were closer together and collided more often. Each collision could bring two black holes together. Over time, repeated mergers could build monsters far faster than slow feeding alone. The Vera Rubin Observatory, which will soon map huge numbers of distant galaxies, is expected to give us much better statistics on how common these violent mergers were. There's also the possibility that black holes in the early universe fed in bursts far above what we see today. Dense gas, low metals, and chaotic early conditions may have let black holes gorge themselves faster than our simple models assume. Astronomers at NASA JPL and ESO are running simulations right now to test how realistic these feeding frenzies could be. No matter which explanation turns out to be right, one thing is clear: TON 618 is not a fluke, it's a clue. It's telling us the early universe was wild. Galaxies weren't calm spirals like the Milky Way. They were crashing into each other. Gas clouds were slamming together. Radiation fields were brutal. Black holes were growing like weeds in a storm. And here's where this gets personal. Every atom in your body was made in stars that lived and died in galaxies shaped by black holes. The heavy elements in your bones and blood were forged in stellar explosions that happened in environments controlled by objects like TON 618, even if indirectly. The universe didn't just quietly build life-friendly conditions. It went through violent phases first. Chaos came before calm. There's also a deeper mystery hiding here. Black holes don't just shape matter. They shape time. Near a black hole, time slows down. Near TON 618, time near the event horizon would crawl compared to time out here. If you could hover safely near that boundary, years for you could pass, while centuries or more pass for the rest of the universe. This isn't sci-fi. It's straight from Einstein's equations, confirmed by experiments and used every day in GPS systems that have to correct for time dilation, work pioneered by scientists working with NASA and Stanford. So TON 618 isn't just big in space, it's big in time. It warps the flow of time itself on scales we can barely picture. And that leads to one last unsettling thought before we go further. Objects like TON 618 may be rare, but they are not unique. The universe seems perfectly comfortable creating things that sit right at the edge of what physics allows, which raises a question we're still afraid to ask out loud. If the universe can build black holes this big, what else can it build that we haven't found yet? Now, let's take this one step further, because TON 618 isn't just a curiosity, it's a stress test for everything we think we know about how the universe works. When astronomers first measured TON 618's mass, teams cross-checked the numbers using different methods. They looked at how fast gas clouds orbit around it, how wide the emission lines are in its light spectrum, and how bright the quasar is across radio, optical, and infrared wavelengths. Data from the Hubble spectrograph, radio surveys linked back to legacy Arecibo observations, and more recent infrared studies from the James Webb Space Telescope all point in the same direction. This thing really is tens of billions of times heavier than our Sunday. There's no easy way to shrink that number without breaking the observations. So scientists asked a tougher question. If black holes like this exist, how many are out there? TON 618 is bright, which makes it easier to find. But for every blazing quasar, there may be many similar monsters that are quiet, not actively feeding, and therefore almost invisible. Black holes only shine when they're eating. When they're not, they hide in plain sight. This means the universe could be packed with giant black holes that we simply don't see yet. The Vera Rubin Observatory is about to change that. When it comes fully online, it will scan the entire sky again and again, watching how stars and galaxies wobble and brighten. Tiny motions in starlight can reveal the pull of invisible, massive objects. This is how astronomers found evidence for the black hole at the center of our own galaxy, Sagittarius A, with work led by teams connected to UCLA and the Max Planck Institute, later confirmed by the Event Horizon Telescope collaboration. The same tricks, but on a much larger scale, may reveal hidden giants like TON 618 across the cosmos. And here's the unsettling part. Black holes don't just sit at the centers of galaxies like passive anchors. They shape how galaxies grow. When a black hole is active, it blasts energy into its surroundings. This feedback can heat up gas and stop new stars from forming, or sometimes compress gas and trigger star birth. It's a messy push and pull. Astronomers at ESO and NASA JPL have watched this happen in closer galaxies with supermassive black holes millions of times the Sun's mass. TON 618 is doing this on steroids. Imagine a galaxy trying to form stars while a central engine is pouring out the energy of trillions of suns. That galaxy's fate is being decided by the black hole at its heart. Too much energy, and the galaxy gets starved. Too little, and it may grow too fast and collapse into chaos. The universe isn't gentle. It regulates itself with violence. This might explain something else that has puzzled astronomers for years. Why do galaxies and their central black holes seem to grow together in a tight relationship? The mass of a galaxy's central black hole is strongly linked to the mass of the galaxy's central bulge. This connection seen in thousands of galaxies studied by the Keck Observatory and the Hubble Space Telescope, suggests black holes and galaxies co-evolve. They grow up together, like dance partners who can't move without affecting each other. TON 618 represents the extreme end of this dance. Its host galaxy must be enormous, or at least it was when the light we see left it billions of years ago. And that means something else. Early galaxies were building monsters fast, way faster than we expected, which points to a deeper gap in our understanding. The early universe may have had physical conditions we don't fully capture in our models yet. Dark matter halos may have collapsed differently. Gas may have cooled faster. Radiation backgrounds may have been stronger. All of this changes how quickly black holes can grow. Teams at the Harvard Smithsonian Center for Astrophysics and Stanford are now building simulations that include more of these effects, using data from JWST and future Vera Rubin surveys to test which scenarios match reality. So TON 618 isn't just a big black hole. It's a message from the young universe saying, your story about how I grew up is incomplete. And the more we find objects like this, the louder that message becomes. Let's zoom in on something that almost never gets talked about outside research circles. How close TON 618 is to the absolute limits of what physics even allows. There is a theoretical ceiling called the Eddington limit. It's the point where the outward pressure of light pushing away gas balances the inward pull of gravity dragging gas in. If a black hole tries to eat faster than this limit, the radiation it produces should blow the food away like a fire hose pushing back water. In simple terms, black holes aren't supposed to grow too fast because their own brightness should choke off their meal. TON 618 looks like it laughed at that rule. When astronomers estimated how fast it must have grown to reach 66 billion solar masses so early in cosmic history, the math didn't behave nicely. Even if it fed at the Eddington limit non-stop from the moment the first black holes formed, it would still struggle to get this big in time. This is one of those moments where the universe seems to say, your limits are not my limits. So how did it do it? One idea is that early black holes formed from much bigger seeds than we assumed. Instead of starting as small remnants of the first stars, maybe some black holes were born already massive, collapsing directly from giant clouds of gas. This direct collapse idea is being studied by teams at the European Southern Observatory and modeled with data inputs from JWST. If that's true, TON 618 may not have started small. It may have started huge. Another idea is that black holes in the early universe could feed in short, violent bursts that briefly exceed the Eddington limit. These superfeeding phases would be unstable and messy, but they could allow rapid growth before radiation pressure pushes material away again. Observations of distant quasars by the Hubble spectrograph and radio telescopes have shown signs of extreme outflows, suggesting black holes really do go through wild growth spurts. There's also the possibility of mergers. In the crowded early universe, galaxies collided more often. When galaxies merge, their central black holes eventually spiral together and merge too, releasing massive amounts of energy as gravitational waves. The LIGO and Virgo collaborations have already detected black hole mergers closer to home, and future detectors, including space-based observatories, aim to pick up signals from much larger black hole mergers. TON 618 could be the end result of many ancient mergers stacked on top of insane feeding rates. Now here's where things get really strange. Black holes this massive may warp space-time in ways we've never tested before. Near the event horizon, time slows down dramatically compared to faraway observers. For TON 618, the scale of that region is so huge that relativistic effects could shape entire star systems near the core of its host galaxy. Stars orbiting close in would experience time at different rates compared to stars farther out. The galaxy itself becomes a weird clockwork of stretched time and bent space. We can't visit such places, obviously, but we can watch their light. Spectra from the Keck Observatory and data from ESO instruments show extreme gravitational redshift in quasar light, a fingerprint of space-time being stretched by immense gravity. TON 618's light carries that fingerprint, distorted by a gravity well so deep that even the idea of normal physics starts to feel shaky. And here's the quiet horror. Behind the beauty. Black holes like TON 618 are not just giant mouths in space. They are cosmic engines that can decide whether whole galaxies live or die as star-forming systems. If too many of these monsters were active at once in the early universe, they may have sterilized large regions of space, heating gas so much that stars couldn't form for long stretches of time. That means fewer planets, fewer chances for life. So, in a strange way, your existence might depend on black holes not being too efficient at their job. TON 618 shows us the edge of that balance. It's proof that the universe can build engines powerful enough to reshape entire galaxies. And the only reason we get to sit here and talk about it is because most of the universe isn't always that violent. Now let's step back from the monster itself and look at what TON 618 tells us about the universe we live in and about how fragile our place in it really is. When astronomers at the Harvard Smithsonian Center for Astrophysics started comparing ultra-massive black holes like TON 618 with smaller ones closer to home, something unsettling showed up in the data. The biggest black holes don't just sit quietly at the centers of galaxies. They shape how those galaxies grow, breathe, and age. They control the flow of gas like a giant cosmic valve. When a black hole is actively feeding, it releases huge jets of energy, not just light, but powerful streams of particles and radiation that punch through the galaxy. These jets can stretch for hundreds of thousands of light years. The radio lobes we see with arrays connected to legacy Arecibo data and modern radio observatories show that these jets inflate massive bubbles in intergalactic space. Inside those bubbles, gas gets heated and pushed away. When gas is too hot and spread out, it can't collapse into new stars. So black holes don't just eat, they also starve their own galaxies. This is one of the biggest puzzles in modern astronomy. How can something so small in size compared to a galaxy control something so large? TON 618's event horizon, even though it's larger than our solar system, is still tiny compared to the full size of a galaxy. Yet its influence can reach far beyond its home. It's like lighting a match in the middle of a forest and watching the wind carry sparks for miles. This idea of feedback is now a major focus of NASA Jet Propulsion Laboratory models and simulations run with data from Hubble and the James Webb Space Telescope. When Webb looks at young galaxies in the early universe, scientists see signs that star formation turned on hard and then shut down fast. One leading explanation is that early black holes grew fast, blasted energy into their surroundings, and shut off their own fuel supply. TON 618 may be a survivor of that brutal phase, a fossil record of a time when galaxies lived fast and burned bright. And here's the uncomfortable part. If TON 618 had formed in a galaxy like the Milky Way, our galaxy might not look the way it does today. The calm, steady star formation that built planets, oceans, and eventually life might never have happened. The Milky Way's central black hole, Sagittarius A, is massive but quiet most of the time. It eats slowly. It doesn't flood the galaxy with deadly radiation. That calm behavior may be one reason complex life had time to form here. So when you hear about a black hole bigger than our entire solar system, it's not just a cool fact. It's a reminder that the universe has places where life would never get a chance. Entire galaxies can be turned into cosmic deserts by objects like TON 618. There's another layer to this story that's even more mind-bending. Because TON 618 is so far away, we are not seeing it as it is now. We are seeing it as it was around 10 billion years ago. That light left when the universe was young, when Earth didn't exist, when our sun was not even a cloud of gas yet. The monster we see might not even look the same today. It could be dormant. It could have merged with another black hole. It could be even bigger. Or it could be quiet and starved. In a strange way, TON 618 is both a real object and a ghost, a message sent across time, telling us what the universe was capable of when it was young and reckless. There's one more layer to this that changes how you think about black holes forever. We don't just see them. We use them as tools to test the laws of reality itself. When physicists at Stanford and researchers working with data from the Keck Observatory in Hawaii model regions around extreme black holes like TON 618, they're not just asking how big or bright it is. They're asking whether space and time behave the way Einstein said they should. Near something this massive, gravity bends light so strongly that entire galaxies behind it can be stretched into arcs and rings. This effect, called gravitational lensing, has been measured around giant quasars using Hubble spectrograph records and now refined with James Webb's infrared vision. And every time these measurements match Einstein's predictions, it feels like a small miracle. Because TON 618 sits in a gravity regime so extreme that if general relativity were even slightly wrong, this is where it would break first. But here's the twist. In the same region where Einstein's math works beautifully, our understanding of matter breaks down. The plasma swirling around TON 618 is so hot, so dense, and moving so fast that normal physics starts to blur. Particles smash into each other at near light speed. Magnetic fields twist and snap like rubber bands under tension. This is not a place you can recreate in any lab on Earth. Not at CERN, not anywhere. The only lab that can run these experiments is the universe itself. Teams connected to NASA JPL and the European Southern Observatory compare real quasar data to massive computer simulations. These simulations try to track how plasma flows, how magnetic fields grow, and how energy escapes as light in jets. And every time the data doesn't quite match the model, it's a clue that we're missing something deep about how matter behaves when gravity is pushed to its limits. Some physicists suspect that near black holes this large, gravity and quantum effects might start to overlap in ways we've never seen clearly before. We don't yet have a full theory that blends Einstein's gravity with quantum mechanics. TON 618 sits in that uncomfortable gap, a natural stress test for our best ideas. It's like the universe is daring us to explain it. And this leads to a quiet fear that scientists rarely say out loud. What if the rules we use to understand black holes are only approximations? What if TON 618 is showing us that reality itself behaves differently when pushed far enough? The math still works, but maybe it's just a surface-level match. Maybe underneath, space and time are doing something we don't yet have words for. Every new observation of ultramassive black holes chips away at our comfort. They are not just big objects. They are cracks in our understanding. Windows into physics that may be deeper and stranger than anything we've imagined so far. And the more clearly we see them, the more obvious it becomes that we're still standing at the edge of what we know, staring into something that does not care whether we understand it or not. Now let's talk about something that sounds like science fiction, but is actually being studied very seriously. What ultra-massive black holes like TON 618 do to their entire galaxies? TON 618 isn't just sitting there quietly eating gas. Objects this powerful reshape everything around them on scales so large that entire galaxies change their future because of a single black hole at the center. Astronomers at the Harvard-Smithsonian Center for Astrophysics and teams working with data from the European Southern Observatory have shown that quasars can act like cosmic engines. As matter falls into the black hole, not all of it disappears. A huge amount of energy is thrown back out into space in the form of radiation and jets. These jets can stretch for hundreds of thousands of light years, punching through interstellar gas like a blowtorch through fog. This process is called feedback, and it's one of the most important ideas in modern astronomy. Here's why it matters. Galaxies grow by turning cold gas into stars. But when a black hole like TON 618 turns on as a quasar, the energy it releases can heat that gas or even blow it out of the galaxy. When that happens, star formation slows down or stops completely. In other words, the black hole can shut off the galaxy that feeds it. This is one reason astronomers think many giant galaxies become red and dead. They stop making new stars and slowly fade as old stars age and die. The monster in the center may be the reason. Observations from the Keck Observatory and follow-up infrared data from the James Webb Space Telescope show that the brightest quasars often sit in galaxies that look disturbed, stretched, or partially stripped of gas. It's like watching a city that burned too hot and ran out of fuel. But the story isn't just destruction. Sometimes the shock waves from quasar jets compress gas in other parts of the galaxy or in nearby galaxies, triggering bursts of new star formation. So the same black hole can both kill stars in one region and help create them in another. It's cosmic chaos with consequences. And here's the part that messes with your head a little. TON 618 is so massive that it likely grew incredibly fast when the universe was young. Astronomers at the Vera Rubin Observatory and researchers analyzing old Arecibo legacy data have been trying to understand how objects this huge could form so early in cosmic history. There simply shouldn't have been enough time for a black hole to grow this big by slowly feeding on gas at normal rates. This has led to new ideas that are still being debated. Some scientists think these ultramassive black holes may have formed from the direct collapse of enormous gas clouds, skipping the normal step of forming stars first. Others think early black holes may have merged again and again in dense young galaxies, growing at insane speeds. Either way, TON 618 isn't just a record holder, it's a problem. A beautiful, glowing, impossible-to-ignore problem that tells us our story of how the universe grew up is still incomplete. And that's the unsettling part. When you find one object that shouldn't exist according to your models, it means the models are wrong, not the universe. TON 618 doesn't just challenge how black holes grow, it challenges how we think the early universe behaved at all. When astronomers look at objects this far away, they're not just seeing distance, they're seeing time. The light from TON 618 began its journey when the universe was young, chaotic, and still figuring itself out. This means black holes of this size were already active when galaxies were still messy piles of gas and dust. Teams at NASA Jet Propulsion Laboratory, working with Hubble spectrograph records and newer James Webb Space Telescope data, have found that many early quasars appear too mature, too bright, too structured for their age. This echoes the same problem seen with early galaxies. Things in the young universe seem to grow up way too fast. Imagine walking into a forest that was planted last year and finding full-grown oak trees. That's the level of weird we're dealing with. One idea scientists are testing is that the early universe was far more efficient at building giant objects than it is today. Gas clouds were denser, collisions were more common, black holes had easy access to food. In some regions, matter may have collapsed straight into black holes without ever becoming stars first. This direct collapse idea is being studied with simulations run at places like Stanford and with observational hints from the European Southern Observatory. Another idea is that physics itself behaved differently back then. Not broken, just more extreme. Radiation pressure, magnetic fields, and even the way matter cooled could have allowed black holes to feed faster without blowing away their own fuel supply. This is still being debated, and new data from James Webb keeps forcing scientists to tweak their models almost every year. And here's something that quietly changes how you see our place in the universe. TON 618 existed when Earth didn't exist. The Sun didn't exist. Our galaxy was still forming. Yet this black hole was already this huge, already tearing through matter and flooding the universe with energy. Long before any life could look up at the stars, monsters like this were shaping the future of galaxies. So, when we say the universe is old, we're not just talking about age. We're talking about history, a violent history. A history where gigantic black holes carved paths through young galaxies, deciding which stars would be born and which would never exist at all. And we are living inside the aftermath of that ancient chaos. There's another layer to this story that makes TON 618 even more unsettling, and it has to do with how black holes don't just sit there and eat quietly. They shape everything around them, sometimes across entire galaxies. When a black hole grows this massive, it becomes more than a hungry object. It becomes a regulator of cosmic life. The energy pouring out from its accretion disk and jets can heat surrounding gas so much that new stars can't form. Astronomers call this feedback. It's like a cosmic thermostat. Too much growth, and the black hole turns up the heat and shuts down its own food supply. Observations from the Keck Observatory in Hawaii and radio maps tied back to legacy Arecibo data show that many quasars push powerful winds into their host galaxies. These winds can move at thousands of kilometers per second. They sweep away gas, choke off star birth, and change the future of entire galaxies. In some cases, galaxies with active quasars end up aging early, becoming quiet, red, and dead compared to star-forming neighbors. This flips the story we usually tell. We often think galaxies build black holes, but with monsters like TON 618, it's just as true that black holes build galaxies, or at least decide how they grow and when they stop growing. Now picture this. TON 618 is not alone. It's one of many ultra-massive black holes found in the early universe. The Harvard-Smithsonian Center for Astrophysics has cataloged several quasars with black holes billions of times the mass of the Sun, all shining when the universe was less than 2 billion years old. Each one is a sign that whatever process built these giants was not rare. It was common. So the real problem scientists are wrestling with isn't just, how did TON 618 get so big? It's, why did the universe make so many giants so early? That question reaches into everything we think we know about cosmic growth. It affects how we model dark matter halos, how gas cools, how stars ignite, and how early galaxies merge. It's why researchers using data from the Vera Rubin Observatory are so excited. Its wide surveys are expected to find thousands more quasars, letting us see whether TON 618 is an extreme outlier or just the most famous example of a much bigger pattern. And here's the quiet part that hits hard. If the early universe could build monsters this large, this fast, then the universe is way better at building extremes than we ever gave it credit for. When we see TON 618, we're not seeing it as it is right now. We're seeing it as it was more than 10 billion years ago. The light hitting our telescopes today left when the universe was still young, when galaxies were rough, messy places still figuring out their shape. That means the monster you're picturing is a ghost from the past. Whatever TON 618 looks like today, we won't know for billions of years. This creates a strange problem for astronomers. We are trying to understand how something grew so massive so quickly, but we can't watch the full story play out. We only get snapshots frozen in time. It's like trying to understand a person's whole life by looking at a few old photos from their childhood. That's why teams at NASA's Jet Propulsion Laboratory and the European Southern Observatory combine data from many different objects at many different distances. Each quasar becomes one frame in a long cosmic movie. Some frames show young black holes still feeding fast. Others show older ones that have gone quiet, their bright disks faded, their jets switched off. By lining these frames up in the right order, scientists try to rebuild the life story of giants like TON 618. But here's where things get weird. There are black holes in the early universe that already look old. Their feeding seems to have slowed down. Their surrounding galaxies look calm, as if the storm already passed. That suggests these black holes may have grown even faster than we thought, then settled down quickly. The universe didn't just create giants. It created giants that burned hot and fast, then went silent. James Webb Space Telescope observations are starting to spot these calm giants at extreme distances. Webb can see the faint glow of their host galaxies, even when the quasar itself is dimming. This helps scientists estimate how much gas is left to feed the black hole and how much has already been blown away by feedback. So the puzzle deepens. Not only did these black holes grow too fast, some of them also seem to finish growing early. And that forces a new kind of question. What kind of universe builds giants in a hurry and then lets them rest? This is where theories start to stretch. Some researchers think early black holes fed on streams of cold gas flowing along cosmic filaments, like rivers pouring straight into their mouths. Others think massive black hole seeds formed from the collapse of giant gas clouds, skipping the normal star stage entirely. Teams at Stanford have modeled these direct collapse scenarios on supercomputers, showing how a black hole could start life already millions of times the mass of the Sun. If that's true, TON 618 might not be the result of slow growth at all. It might be the result of a head start. In our own galaxy, the Milky Way, the black hole at the center, Sagittarius A, is massive, but it's tiny compared to TON 618. Yet it still shapes the motion of stars in the galactic core. Astronomers at the Harvard-Smithsonian Center for Astrophysics have shown that when a black hole feeds, it doesn't just eat quietly, it fights back. The radiation in jets blasting out from the center can heat gas, push it away, and even shut down star formation across the entire galaxy. Now imagine that effect scaled up to ton 618. This black hole isn't just influencing its galaxy, it's likely dominating it. The energy pouring out from its accretion disk and jets would be enough to sweep entire regions of gas clean, like a cosmic leaf blower. Any nearby clouds trying to collapse into new stars would be blasted apart or heated so much they couldn't cool and form stars at all. That means ton 618 may have shaped the fate of billions of stars before they were even born. This leads to a strange thought. In galaxies hosting ultramassive black holes, the black hole may have grown first, and the galaxy grew around it later. This flips the usual story. We often imagine galaxies forming first, then black holes growing slowly at their centers. But with objects like ton 618, the black hole looks like the main character, and the galaxy looks like the supporting cast. Observations from the Keck Observatory in Hawaii back this up. In some distant quasars, the black hole's mass is far too large compared to the mass of the stars in the host galaxy. The normal balance we see nearby is broken. The black hole is too big for its home. So how do galaxies survive living next to something like this? Some don't. The feedback can be so strong that star formation shuts down early, leaving behind a quiet, dead galaxy filled with old stars. Others might be torn apart by mergers, feeding the black hole even more. This violent back and forth between black hole growth and galaxy growth is one of the main engines shaping the universe. Ton 618 sits at the extreme end of this process. It's like seeing the loudest explosion and trying to understand all fireworks from that one blast. And here's the unsettling part. If the early universe could make many objects, like ton 618, then the universe we live in today was shaped by giants we can barely imagine. The calm galaxies we see now may be the survivors of an early era of monsters. This is why astronomers are racing to find more ton 618 type objects. Every new one is another data point in the story of how the universe grew up. For a moment, take in what ton 618 really means. This isn't just the biggest black hole we've ever found. It's a stress test for the universe itself. A single object so massive that, if you dropped it where our sun is, its event horizon would stretch far beyond Pluto. A gravity well so deep that light falling in never comes back. A power source so extreme that, from across billions of light years, it still burns brighter than entire galaxies. When scientists at NASA's Jet Propulsion Laboratory, working with data from Hubble spectrograph records and follow-up studies from the European Southern Observatory, realized how massive ton 618 truly was, the quiet reaction in research rooms wasn't excitement. It was disbelief. Calculations were rechecked, models were run again, and the numbers still refused to behave. Because ton 618 doesn't just sit there. It exists at a time when the universe was young, messy, and still figuring itself out. According to what we see from the James Webb Space Telescope and long-term quasar surveys from Keck Observatory in Hawaii, black holes this large should not have had enough time to grow so fast. Even if they ate non-stop from the first stars onward, even if they merged again and again, the clock of the early universe still feels too short. That means something about our picture of how black holes form is missing. Either the first black holes were born much larger than we thought, or the early universe was far better at feeding them than our models can explain. And this is the moment where the story turns from impressive to unsettling. Because if the universe could build monsters like ton 618 so early, then the quiet, gentle sky we see today is built on a violent past. Galaxies may not have grown slowly and peacefully. They may have grown under the influence of giants that blasted radiation, bent space, and shaped where stars could even exist. The structure of the cosmic web mapped by surveys from the Vera Rubin Observatory and legacy sky data from Arecibo isn't just a calm pattern of matter. It's the fossil record of ancient battles between gravity and light. Ton 618 is not an accident. It's a survivor of that era, a relic of a time when the universe made things as large and as powerful as it possibly could. So when you look up at the night sky and see calm points of light, remember this: far beyond what your eyes can see, There are places where space is being bent so hard that time itself slows down. There are objects so massive that they rewrite the rules we use to describe reality. TON 618 is proof that the universe doesn't care about what feels reasonable to us. It builds on a scale that dwarfs our imagination, and it has been doing that since long before Earth, the Sun, or even our galaxy existed. If this story stretched your sense of scale, there's another one on your screen right now that goes even deeper into the strangest objects ever found in space. Watch that next, because the universe gets even more unbelievable the closer you look.